Okay. Good morning, dear students. Good afternoon, dear students. So today we'll discuss the earth pressure. So what is earth pressure, where it is existing, and what are the preventive measures that we can take just to resist the lateral earth pressure, right? So first, we will just have some idea about the stable slopes. Now here you can see this is the soil mass. This soil mass is considered to be the sloping ground. This is the sloping ground over which this is a natural hill. Suppose we will assume this is the natural hill. This natural hill is actually, it is in a stable condition. This natural hill is in a stable condition. When the hill is in a stable condition, I is suppose the inclination angle. I is the inclination angle. When this I is less than phi. When this I is less than phi. Now what is phi? Phi is angle of inclination. I is angle of inclination for a slope. And phi is angle of repose. Angle of repose. Now, always remember that this repose angle is an important criteria for the stability of slope. When your I is less than phi, in that case, we can say that the slope is in a stable condition, right? But when this I increases, then the phi, in that case, the slope is unstable. And always remember that the soil over the sloping ground is a very unstable soil mass which is always subjected to failure, right? So therefore this I and phi is an important parameter for the stability of the slope, right? So in this case, now this is the natural hill where we are just wanted to construct the structure. Suppose I want to construct the structure of a road, right? So what we do, and if there is a space limitation, so what I will do, I'll just remove these soil mass. Suppose this is the stable slope, I just remove this soil mass. So naturally, in this case, this is the soil which is unstable in condition, which is unsupported soil mass, and it is unstable because over here the stability of the slope we have removed. I just wanted to construct the road over here. For that, I have just removed this portion of the slope. Now, this is the unstable soil mass and which has a tendency to move or slide down the soil surface in this road. So, in that case, we will provide an artificial structure. That may be constructed with the masonry, it may be a concrete or it may be a masonry structure. Concrete or masonry wall. This concrete or masonry wall, what is basically the function of this wall? This function or this wall is basically resisting the forces or resisting the lateral earth pressure which is developed by this. Now this is the soil mass which is the unsupported soil mass. This unsupported soil mass has a tendency to give its pressure to the adjacent support. So this is unsupported soil mass, will exert the pressure, give the lateral pressure to the retaining wall. This retaining wall is an artificial structure constructed with the help of a masonry or it may be a concrete structure, right? So this is the pressure which is called as active earth pressure. Active earth pressure. So what is retaining wall? Retaining wall is a artificial construction made up of a concrete or masonry which is used to resist the lateral pressure of the unsupported soil mass. So this is basically the retaining wall. So where it is being constructed? This is being constructed over the unstable soil mass where it is not possible to extend the stable slope, or where I is less than phi. In that case, we will provide this is the artificial support, right? Artificially constructed support just to resist the lateral earth pressure into the soil. So this is retaining wall. Now we will just see the different components of the retaining wall. This is the retaining wall. Now we see there are different components of the retaining wall. I just draw the diagram. I just draw the diagram over here. So here this is the artificially constructed retaining wall which has a base. Now in this case, this is considered as a backfill zone. The soil which is retained by the retaining wall is called as backfill. What are the properties? That backfill may be the soil, it may be coal, it may be water, whatever it may be. So whatever portion of the material retained by the earth or retained by the retaining wall is called as backfill. Now backfill has different properties. That important properties are gamma, phi and C. What is gamma? Gamma is the density of the soil, density of backfill. And what are the shear strength parameters? C is cohesion and phi is angle of shearing resistance. So these are the two important shear strength parameters. These are shear strength parameters, right? So this is the backfill soil. Now here this soil is called as a retaining wall, or sorry, this structure is called as the retaining wall. This is called as retaining wall. Now there are two components which are considered to be the most important component, that is a backfill, and the another is the artificial structure which is called as retaining. Right? In addition to that, there is one more parameter which we have taken into consideration. Now, as we have seen in the previous diagram, the soil may be like this, the portion of the hill may be like this. Now, in this first assumption, we have considered that this backfill is a horizontal backfill. Now, what about the portion which is placed above the horizontal backfill? This portion of the soil we are considered as an equivalent surcharge. Suppose here we will consider this is the average height of the inclined backfill. This is the average height of the inclined backfill, and suppose this is the density of the backfill. Density of the backfill and the average height of the backfill. So these will be combinedly we will use as a surcharge. This H dash is the average height of the inclined backfill and density, that is gamma is the density, average density of this inclined backfill. We will consider this product is a Q, and that Q is the equivalent surcharge load, and that equivalent surcharge load we will remove it and we will place it over the top of the horizontal backfill, and it is denoted with Q. So this Q is surcharge. This Q is surcharge, which is gamma into H average. So these are the three components of this retaining. Now here, the soil is subjected to pressure. This soil is unsupported soil mass, which is always subjected to some pressure, and that pressure is called as active earth pressure, which is denoted by PA. That is the active earth pressure. Now, this active earth pressure will try to push the wall away from the backfill. These will try to push the wall away from the backfill. Is it possible every time? Have you seen it anywhere? Due to the backfill zone, wall moves away from the backfill. Naturally not, because there is one resisting force which is coming from the opposite direction and which will not allow the wall to move. Which is not allow the wall to move, which is just push the wall towards backfill, and that is called as passive earth pressure. So always remember that there is some embedment in the form of foundation. There is some embedment of the soil in the form of foundation. So these will be act as a foundation of retaining wall. And this foundation soil, and the second important is the sulfate of the retaining wall. these two will be combinedly act as a passive earth pressure, and that passive earth pressure will not allow the wall to move. It will just occurring in this direction, and this is called as PP. This is called as PP, that is the passive earth pressure. And always remember that passive earth pressure is having more numerical value as compared to active earth pressure, and therefore your wall is in a stable condition. Right? So this is about the retaining wall, active earth pressure and the passive earth pressure. Now we will discuss the different types of pressures. Right? This is types of earth pressure. Types of earth pressure. So there are three types of earth pressure which we are taking into consideration. First is at rest pressure. Then second is active earth pressure. And third is passive earth pressure. Right? So there are three earth pressure. First is the very important at rest pressure. At rest pressure means there is no wall movement. There is no wall movement of a structure, then it will be called as at rest pressure. Then there is the active earth pressure. Active earth pressure is the pressure which moves the wall away from the backfill, and passive earth pressure is the pressure which push the wall towards them. Right? So first we will discuss about the at rest pressure. At rest pressure, or it is also called as pressure, earth pressure at rest, or pressure at rest. Right? So in this case, if there are a properly supported or anchored retaining wall. Now suppose we will just assume the breach depth. We will just assume the breach depth. Now suppose here we can see this is the bank of the river. This is the bank of the river, and here there are two supports. That end supports of the breach is called as the abutment, whereas these are the two end supports of the retaining of the dam, of the breach. These are the two end supports of the breach. Now here there may be an intermediate support. The intermediate support is called as pier, right? But we are just concerned about the end support because that end supports which are called as abutment, or these are the retaining wall. Why this is retaining wall? Because it retains the soil on its side. You can see this is the side. Why it is considered as a retaining wall? Because that end supports of the breach is also act as a retaining wall, because it is retaining the clay or retaining the soil or any material from its boundary, right? Then these two end supports are connected or anchored down with a single member, and that single member is called as breach deck. So here you can see this is the breach deck. This breach deck or the horizontal slab, that horizontal slab supports or horizontal supports anchor the two surface. जो retaining wall है, दो retaining wall को उसने अच्छे से anchor करके रखा हुआ है, and therefore even though there is a pressure of the soil on its both the sides, still no movement of the wall is taken place. क्यों नहीं हो रहा है? क्योंकि ऊपर से उसको पकड़ के रखा है, ब्रिज डेक के स्लैब ने उन दोनों रिटेनिंग वॉल को ऊपर से बांध के रखा है, पकड़ के रखा हुआ है, एंड देयरफॉर इवन दो देयर इज अ एक्टिव वर्क प्रेशर एक्टिव ऑन बोथ द साइड, still there is no movement of the wall, and this is the case no movement of wall. then this is called as the earth pressure at rest. Means the soil pressure is there, but due to that soil pressure, the wall movement is not coming into the wall because it is just anchored down. Both the supports are anchored with a single member, and here that is the bridge there. The another example of this type of earth pressure at rest, you can see the walls of the swimming pool. You can see the walls of the swimming pool which are supported with the horizontal, with the bottom slab, right? That bottom slab connect the two vertical members, and therefore the same example we can say it is for the swimming pool walls. So this is at pressure condition. Then second is active earth pressure. Second is active earth pressure. Active earth pressure. So this pressure, active earth pressure, is denoted by PA. Now again, what we will consider here, we will just assume a retaining wall. We will just assume the retaining wall. This retaining wall retains a backfill. Retains backfill. Now, there is a pressure. Now, suppose I just draw a bigger diagram, in which case we will just consider this is the retaining wall. This retaining wall retains a backfill. Now, this is the horizontal backfill. Suppose I will assume H is the height of the retaining wall, right? Which supports the backfill. Now here, if the pressure increases, naturally the soil is fixed, and there will not be a sudden collapse. There will not be a sudden failure of the soil. Soil may fail through a weaker plane. Soil may fail through a weaker plane, any weaker plane or anything from which some properties may be lacking, or due to that the weaker plane or the weaker pocket may be formed. If there is a weaker plane, so soil must be filled through that weaker plane. And here, suppose we will assume that this is the weaker plane. This is assumed to be the weaker plane. Now, naturally, soil has a tendency to fail through a weaker plane. So here, this weaker plane will be considered as a failure plane. Here, considered it as a failure plane. Now, if the soil mass is failed through this section, in that case, this portion of the soil mass is assumed as an unsupported soil mass because that is a failure wedge. So this is a failure wedge. This failure wedge is a unsupported wedge, or it is an unsupported soil mass. This is unsupported soil. Now, if there is an unsupported soil mass, that unsupported soil mass has a tendency to move towards gravity. So, this soil mass has a tendency to move in the direction of gravity, and therefore, this will move in the direction of gravity. If suppose this unsupported soil mass, a huge soil mass, unsupported soil mass slides down. Unsupported soil mass slides down, naturally, what will happen? This will push the wall away from the backfill, and in that case, the movement of the wall is taken place like this. There is a movement of the wall. So this is the movement . This is movement of the wall. So movement of the wall in which direction? Movement of the wall in the direction away from the back. This is the case of active earth pressure when the soil is faced through a weaker plane. Then this will be considered as an unsupported soil mass, and unsupported soil mass has a tendency to move towards gravity. When this loose soil mass comes into the direction of gravity, this will push the wall away from the backfill, and there is a movement of the wall, and this is the case of active earth pressure. Right? Now, the third one is a passive earth pressure. Third is passive earth pressure. And which is denoted by PP. Which is denoted by PP. Again, the same diagram we considered. And consider a same diagram. So, once this active case is taken place, and naturally there will not be a movement of the ball away from the backfield because there is one more force which is coming from the opposite direction, and that is called as PP. So this PP, what will do? This is the first case when ball moves towards backfield. Away from the backfield. This is the condition which is taken place due to the active case of the soil, and soil mass becomes moved down. Now there is a passive force which is just oppose this movement of the soil mass, and it will just lift up the soil mass in this direction. And this is the case of passive earth pressure, where ball again take its original position, and there is a movement of ball towards backfield. Right? So these are the three cases, that is active, passive, and the earth pressure at rest. So this concept of active earth pressure has been studied by Rankines. This concept of active earth pressure has been studied by Rankines, and he has just made a simple assumptions. So first assumption in Rankine's theory, he has made a first assumption in Rankine's theory, that Rankine's theory is first soil is homogeneous and isotropic. Soil is homogeneous and isotropic. Soil is homogeneous and isotropic. Then wall is vertical. Then soil is or backfield is dry and cohesionless. Backfield is dry and cohesionless, and fourth is horizontal backfield. Horizontal backfield is assumed. So the soil under consideration, backfield soil under consideration, is taken as a homogeneous and isotropic, means there is no layered soil, right? Then in the second case, wall is assumed to be the vertical or nearly vertical. Exactly, it may not be inclined, it may be vertical or it may be a slightly vertical. Then the next is, in the previous case, soil is considered as a dry cohesionless backfield. Dry cohesionless. What is meant by cohesionless? Cohesionless means the sand is taken into consideration. That is, the dry sand is taken into consideration, and in another case, horizontal backfield is assumed. Right? So these are the assumptions previously made, and further the analysis has been extended for the clay soil and for different cases of wall soil systems. Right? So first we will see the Rankine theory, how the equation has been derived. Right? So in this case, what Rankine's theory says? So here, what we have assumed, this is the retaining wall. This is retaining wall of height h. Then this is the horizontal backfield. What he has assumed? There is a horizontal backfield, means no inclination is taken into consideration, and backfield is sand. Backfield is sand. If the backfield is a pure sand, in that case, which parameter will be 0? the cohesion component will be total 0, and therefore here we are considering C is equal to 0, and what are the properties? It will be a phi and gamma are the properties of the soil, right? So in this case, he has assumed certain point P. He has assumed certain point P at a depth Z. He has assumed this is Z depth and P is any point at depth Z, right? Now, at point P, what are the different pressures which are expected? The pressures, any object, right, we are considering. Suppose we have considered a small object which is some distance below the ground level. So naturally over there are एक तो ये unsupported soil mass है और दूसरा some depth below the ground level. This is below the ground level and this is with the unsupported soil mass. If it is unsupported soil mass, means naturally there must be a horizontal pressure that is in the form of active earth pressure, and another pressure is due to the surface of the soil which is placed above this one, right? So there are two forces, two pressures which are acting. So first we will consider as sigma B, and the another we will consider as sigma H. Now tell me, what is sigma B? Sigma B is the vertical pressure due to the surface of the soil. Now, what is the, how we will get that the sulfate? That sulfate is equal to weight, it's equal to volume multiplied by density, right? So, what is weight? Weight is equal to volume multiplied by density. Density of vacuum. In this case, volume is area multiplied by Z and density is gamma. Now, area we are considering as unit, and therefore this is gamma into Z. This is gamma into Z. So here we will just consider this is gamma into Z. Then what is sigma H? Sigma H is the horizontal pressure over the unsupported soil mass, and in this case that is considered as PA. That is considered as PA, right? So these are the two pressures which are acting over the any soil mass at any depth Z, and that is considered as P. Now, here, what is the equation of a plastic equilibrium of a soil? So, what is the equation of the plastic equilibrium of soil? And that is sigma 1 is equal to sigma 3 tan square alpha plus 2c tan of alpha. This is the equation which we have already discussed in geotechnical engineering 1, and this is called as Bell's equation. So what is this? Is sigma 1 is equal to sigma 3 tan square alpha plus 2c tan alpha. What is sigma 1? Sigma 1 is the major principal stress, sigma 3 is the minor principal stress, alpha is the angle of failure. What is alpha? Alpha is 45 plus 5 by 2. This is alpha. Then what is C? C is the cohesion of the soil. Now in this case, sigma 1, as we have discussed, sigma 1 is major principal stress, sigma 3 is minor principal stress. Now tell me, out of these two, which will be assumed as major and which will be assumed as minor? At this moment, we don't know which is major and which is minor. But here we have assumed that this is the case of a active earth pressure. Now suppose I am just applying the pressure over here. This is the soil mass and I am just applying the pressure over here. What is happened? The pressure will be maximum. Once the wall moves, there is a release of the pressure. And if the pressure is released, so which one will be a minimum one? So in this case also the same thing we discussed. This is the soil mass and I am just applying the horizontal pressure. The horizontal pressure is maximum up to which there is no movement of the wall. But at the moment the soil or the wall is getting moved, in that case this pressure is getting released, and therefore this PA is assumed as a minor and this sigma B is considered as major. Therefore this is assumed as sigma 3 and this is assumed as sigma 1. That sigma 1 is a major principal stress and this is the minor, right? So in this case we will assume the same thing. So in this case I just write down and rewrite the equation. This is sigma H, which is PA. So in this case, sigma P will be considered as gamma into Z. Then sigma 3 we will assume as PA, that is tan square alpha plus 2C tan of alpha. Now again, as the soil is considered as a sandy soil, sand is C is equal to 0. As we have assumed in the assumption itself, the soil is considered as a sand, therefore C is equal to 0 and therefore this component is equal to 0. This component is equal to 0 and therefore the same equation is becomes gamma into Z is equal to PA into tan square alpha. Right? So in this case, now we are interested to find out the value of PA. So here it will be PA is equal to gamma into Z upon cot square alpha. So here I just write down PA is equal to gamma into Z tan square alpha and it will be a cot square alpha. So here I'll just take this alpha is equal to 45 plus 5 by 2 and in that case it will be found that alpha is 45 plus 5 by 2. So in that case this PA is equal to gamma into Z 1 minus sin phi upon 1 plus sin phi. Right? So this is called as Ka. This is called as Ka. This constant that is 1 minus sin phi upon 1 plus sin phi is considered as a Ka. That Ka is coefficient of active earth pressure. Right? This Ka is coefficient of active earth pressure. Right? So at this moment we will just assume that I just rub this out. And just consider this is Ka. So at Z there, at depth Z, at depth Z, what is the pressure? Small Pa is equal to Ka into gamma into Z. Ka into gamma into Z. Now, at the top of wall, what is Z? At the top of the wall, Z is equal to 0. At the top of the wall, Z is equal to 0. Therefore, this equation PA is equal to 0. Right? Then, at the bottom, of the wall, this Z is equal to H. Z is equal to H, and therefore this PA is equal to Ka into gamma into H. Now tell me whether the pressure is increases with the depth or not. Now you can see where the Z is 0, the pressure is 0, and at the bottom where Z is equal to H, the pressure is maximum. Means from this we can say that the pressure is increases with the depth, 0 at the top, maximum at the bottom. Right? Means it is increases with the depth, it is increases with the density. Because sandy soil has a tendency to just give a pressure. Just imagine when we make the excavation into the sandy soil. Anything you observe, we have to provide an immediate support when we are making the excavation into the sandy soil. Whereas in the clayey soil can be stand unsupported up to certain depth. After that, we have to provide a support. Right? So in this case, from this observation, you can say that the pressure is 0 at the top and maximum at the bottom. So I'll just remove this part. In this case, so I'll just draw a pressure distribution diagram. I'll just draw a pressure distribution diagram of the retaining wall. So here this Z is equal to 0. As Z is equal to 0, the pressure is 0. Therefore, this PA is 0 at the top. Then I'll just consider any depth Z at which the pressure is PA into gamma into Z. And at the bottom, the pressure is maximum. And here you can see this is Ka into gamma into H. So this is the maximum pressure at the bottom because sandy soil exert the pressure immediately because it cannot stand unsupported. Without support, it cannot stand. Therefore, it exerts the pressure over the retaining wall, and therefore, when the Z is equal to 0, the pressure is 0. When Z is equal to H, pressure is maximum. So, in this case, then the magnitude of active earth pressure. The magnitude of active earth pressure is the area of pressure distribution diagram. Pressure distribution diagram. And what is this pressure distribution diagram? This pressure distribution diagram is a triangular pressure distribution diagram, and therefore the PA, that is the magnitude of active earth pressure, is half of Ka into gamma into H into H. So here this is the magnitude of maximum earth pressure, and which will be taken as kilonewton per meter run. Kilonewton per meter run. Right? So here, now tell me where this pressure will be at. Where the CG of the triangle is at? The CG of the triangle is at h by 3 distance at the bottom. So here it will be at h by 3 distance from the bottom, and this is the maximum earth pressure or the magnitude of maximum earth pressure which will be acting at the 1/3 distance or h by 3 distance from the bottom. Is it clear to all? Now, after this, we will consider a different cases of active earth pressure, right? So this is the simple case when there is a dry cohesionless backfill without any surcharge, without any water table, and without any layered soil deposit. Further, the first theory which has developed for a homogeneous isotropic sandy soil which is dry cohesionless, right? Then the same theory has been extended for the different cases of earth pressure, and that we will discuss now, right? So first case is a simple case. So here we will assume that case 1. So this is case 1. So this case 1 is equal to, here we will assume this is the height of the retaining wall H, then this is backfill. This backfill is a dry cohesionless backfill where gamma and phi are the properties. Here it is considered as sand, therefore C is equal to 0, right? You can just assume that the pressure is 0 at the top and maximum at the bottom. So this case we have discussed right now. So what is the bottom ordinate? It will be increases with the depth. So here it will be Ka into gamma into H. P is 0, right? So what is Ka? Ka is 1 minus sin phi upon 1 plus sin phi. So this is K is called as coefficient of active earth pressure. This Ka is called as coefficient of active or pressure. So in this case, we will just calculate the active or pressure. So what is the magnitude of maximum PA? This PA is the area of Ka into gamma into H multiplied by H. So here it will be PA is equal to half of Ka into gamma into H square. So this is the magnitude of maximum earth pressure, and it is at H by 3 distance from bottom. H by 3 distance from the bottom. So this is the first case, right? Now, if suppose we have assumed that if the soil is becomes submerged, if the soil is becomes submerged, soil is becomes submerged means the water table rises and reaches to the ground level, right? So that is the critical worst condition. That is the critical worst condition when entry of the water content, as we know, water is an enemy of soil engineering. Water is an enemy of soil engineering. The strength reduced to 50% when the water enters into the soil. That is in case of the strength. But here, when the backfill is becomes submerged, the pressure may increases to 50 to 100%. 50 to it may be twice. The pressure may increase to 2 times or it may be 3 times when water enters into this bed, because in this case the soil loses its strength and the stresses are increases. So that is the critical worst condition where the water table existing in the backfill zone, right? Therefore, when we are always, the efforts are taken to remove or the lower down the water table as early as possible for the economical design of the retaining wall, right? So that is the worst condition of the retaining wall when the soil is becomes submerged, means the water table reaches to the ground level, right? So I'll just draw the diagram of it. Case 2. Second case. Case 2, when submerged backfill. Submerged backfill. When water table reaches to the ground level. Now in this case, what we have assumed? Water table reaches to the ground level. If suppose water table reaches to the ground level, backfill is becomes submerged. When the backfill is submerged, the submerged density is calculated as gamma saturated minus gamma W. So what is gamma W? Gamma W is unit weight of water. Weight of water. So what is the unit weight of water? Unit weight of water is generally taken as 9.81 or generally it is assumed as 10 kilonewton per meter cube. Right? So this is the soil is in a submerged condition. This condition is considered as a critical worst condition where pressure increases to double or it may be triple. And therefore, we are always trying to lower down the water table, and therefore, the deep holes are provided over here. And these deep holes are in this nature. These deep holes are provided with the inverted filters. These are inverted filters. This is deep holes. These deep holes are generally provided across the retaining wall and it is generally staggered manner. Where the center to center distance between the deep holes is 1 to 1.5 meter. Generally, एक दूसरा यहाँ पर तीसरा यहाँ पर like this. It is provided in a staggered manner where the center to center distance between the deep holes are 1 to 1.5 meter depending upon the condition of the soil. Then, just to remove, just to stop the escape of the backfill material, these are provided with the inverted filter and these are inclined downward. So whatever water enters over here, that can be removed as early as possible and just to lower down the water table so that the earth pressure can be reduced. Right? So here, what are the different pressures which are acting? Again, the pressure will be maximum at the bottom and zero at the top. But here, the first pressure is due to the submerged unit weight of the soil. Because the soil is submerged over here, so the first pressure is due to the submerged unit weight of the soil, and therefore it will be Ka into, instead of gamma, now it will be gamma submerged multiplied by H. And in addition to that, in addition to the submerged soil bed, there is a water pressure also, and that water pressure is also at in a triangular manner, zero at the top and maximum at the bottom. Whereas the intensity is gamma W into H. Now in this case, what is the pressure? Total pressure or the magnitude of maximum earth pressure is equal to half of Ka into gamma dash into H plus gamma W into H multiplied by H. So here we are considering the total area of both the pressures. It is gamma submerged. Always remember that this is become gamma submerged. This is become gamma submerged, and here they are taking the water pressure, and that will be gamma W into H. So the area of the triangle, and again it will be acting at the distance. So this is PA, and it will be acting at a distance of H by 3 from the bottom. So this is the second case, and this is assumed to be the critical worst condition of the soil, right? Then the third case. Case 3. Here, the case 3 is the soil containing surcharge. Soil having surcharge. Soil having surcharge above the horizontal backfill. Soil having surcharge above the horizontal backfill. Now here we will just assume that this is the retaining wall. This is the retaining wall. Now here, this is retaining wall, which is again we will consider as a H is the height of this retaining wall. This is the horizontal backfill. Many times, if suppose this is the condition where there is an inclined backfill, so that inclined portion of the wall, inclined portion of the backfill is assumed as a surcharge, which is this inclined backfill is replaced with the equivalent surcharge load of intensity Q, right? So here, just this portion is removed and it is placed at Q is equal to, or whatever Q is surcharge. Now, again the soil backfill is a sandy soil, which is properties are gamma and phi. Now in this case, as we know, the first pressure is due to surcharge will be acting over this portion of the wall. Over this portion of the wall, one, the pressure is due to the backfill soil. Pressure is due to the backfill soil, which will be a triangular distribution, 0 at the top, maximum at the bottom, and another pressure that will be act as a surcharge pressure. Now, above the backfill, this surcharge is there. Above the backfill, this surcharge is placed directly. So, this surcharge pressure will be act throughout the backfill zone. It will be act throughout the wall section. And that will be same over here, it will be same over here, it will be same at the bottom. And therefore, the pressure due to this surcharge will be same throughout. Over this retaining wall, The pressure will be same over here, the same pressure will be over here due to surcharge, and the same pressure will be over due to surcharge, and therefore the pressure distribution due to surcharge is a rectangular because it will be act uniformly throughout the body, right? And therefore the first pressure distribution is a rectangular pressure distribution. This is of intensity Q into Ka. Q into Ka. What is Q? Q is the surcharge and Ka is the coefficient of active work pressure, which will be placed above the backfield, and that will be uniformly acting over the whole volume. The same pressure will be over here, same over here, and the same over here. Therefore, the pressure distribution diagram is rectangular. Then the another pressure distribution is diagram that is due to the backfield zone. Again, it will be 0 at the top and maximum at the bottom, and the bottom intensity will be Ka into gamma into H. Ka into gamma into H. Now what we'll do, we'll just have a combine, we'll just combine these two diagrams. First diagram is due to the surcharge and second diagram is due to the backfield. Right? So what is the total pressure and where it will be at? So first we will determine the TA is the area of first distribution diagram plus the area of second distribution diagram, that will be combined. Right? So what is the area of the rectangular? So in this case, this PA is equal to Q into Ka into H plus half of Ka into gamma into H square. So first, this is the area of the rectangle and this is the area of triangle. Now, you can do one thing, you can just calculate the area, you can make the combined diagram and you can calculate the area of the trapezoidal, and you can just directly get where the CG of the trapezoidal will be at. Now, where it will be at? So Z bar is the distance at which the total pressure will be at, and that is, we will just calculate this Z1. Z1 is the CG of the rectangle. It will be at H by 2 distance from the bottom, and here this we will assume that Z2. So here this Z2 is equal to H by 3 distance from the bottom. Z2 is H by 3 distance from the bottom. H by 2 here, H by 3 over here. So the combined CG of both the diagram, you can calculate it by Z bar, and that is A1 into Z1 plus A2 into Z2 divided by total, or it will be A1 plus A2. Where what is A1 and what is A2? A1 is the area of the first distribution diagram and A2 is the area of the second distribution diagram. Is it okay? So here, this combined pressure will be acting somewhere here and it is denoted by Z bar distance from the bottom. Is it okay? So this is the third condition where there is a surcharge. Now we will just assume that there is a partially submerged backfield or there is a layered backfield, right? So the third case we will assume it as partial submerged backfield. Case 3. Case 3. Partially submerged backfield. Partially submerged backfield. Now here, again the same thing we will consider over here. H is the height of the retaining wall. So in this case, this is backfield, and here backfield is partially submerged, means somewhere here the water table is high. In this case, we will assume it as a two-layered backfield. Here we will consider the H1 is the H1 is the height up to which there is a soil is a dry or saturated soil. And naturally, below this, we will assume it as H2. H2 is the distance at which the soil is submerged. Submerged soil, and here we will just consider gamma submerged, right? So here the first is the case which is similar to the first case. First layer is similar to the first case when there is a dry cohesionless backfill. Here we are considering two layers because in the upper layer the soil is in a dry condition, whereas in the bottom layer, due to existence of the water table, the soil is getting submerged. Right? So in this case, the first pressure in the first layer, that is the dry cohesionless backfill, and it is similar to the case 1. And therefore, the intensity becomes Ka into gamma 1 into H1. Ka into gamma into H1. So this is the simple case that of the 1. Now, here over the second layer or this portion of the wall, over this pressure portion of the wall, the sulfate of this soil will be acting throughout, and then second pressure, that will be the triangular pressure distribution 0 at the top, maximum at the bottom. Now first pressure that will be assumed as a surcharge, the sulfate of the soil will be assumed as a surcharge, and which will be acting over the interface of first and second, right? So we will just consider this soil is act as a surcharge. This soil is act as a surcharge, and Q is equal to gamma into H1. The intensity, Q is the intensity, or this will be the sulfate of the soil which is available in the first layer will be act as a surcharge plate which have to be placed over the interface of first and second layer, and then will be act as a surcharge where is the intensity Q is equal to gamma into H1 is the intensity of that, right? Again, when there is a surcharge, just remember, when there is a surcharge, the surcharge will be act throughout the depth, it will be same. This surcharge will be same throughout the depth of the wall, and therefore the distribution diagram is a rectangular distribution diagram which will be acting over the second layer, and here this is the intensity. What is this? It will be Q into Ka. Q into Ka. What is Q? Q is equal to gamma into H1. Right? Then again, this pressure is due to the submerged soil weight, and another is the water pressure. So this is the case which is similar to the second case where the soil is in the completely submerged condition, and therefore the distribution diagram is like this. So it will be Ka into gamma submerged into H2, and there is a water pressure where the intensity is gamma W into H2. Intensity is gamma W into H2. Now, how many diagrams you are having? You are having one. There is a diagram due to surcharge, and there is a third one. So, what is total PA? Total PA is the area of first distribution diagram, second distribution diagram, and third distribution diagram. Then we have to calculate the individual Z1, Z2, Z3 for the different diagrams. That is the CG of the different diagrams from the base of the footing, and therefore this is A1. This is A1, which will be acting at Z1 is equal to H2 plus H1 by 3. Are you agree? Z1 is equal to H2 is the distance, then here it will be H1 by 3, right? Then the CG of the second diagram will be again at over here, it will be A2, and that is H2 by 2. And the third, A3, it will be H3 by H2 by 3. Are you getting it? Now again with the same way, we will calculate what is PA then. What is total PA? So PA is equal to A1 plus A2 plus A3. So what is A1? PA is half of KA into gamma into H1 square. Right? Then plus area of the rectangle. Area of rectangle is Q into KA into H2. That will be Q into KA into H2. And the third is half of KA into gamma submerged into H2 plus gamma W into H2 into H2. So by this way, we will just calculate the total PA. Then Z1 you are having, Z2 you are having, and this is Z3. So all Z1, Z2, Z3 you are having. Now we calculate the value of Z bar is equal to A1 Z1 plus A2 Z2 plus A3 Z2, and it is totally divided by A1 plus A2 plus A3. So here the combined CG will be at a Z bar distance from the bottom. Right? Now we will have the last case, that is the layered method. Last case, that is layered soil or layered method. So this layered method is the case 4. This is case 4. Now here I will assume there are 2 layers, and this is total H, that is the height of the retaining wall. H1 is the first layer of the retaining wall, H2 is the second layer of the retaining wall. Right? So here the soil parameters are gamma 1 and phi 1, whereas here it will be gamma 2 and phi 2. Right? Now in this case, it is the similar case as that of the first one. So in this case, this pressure distribution diagram is Ka 1 into gamma 1 into H1. So this is the first pressure distribution diagram, which I have denoted with the 1. Then this sulfate of the soil layer will be act as a surcharge over the interface of the first and second layer. Means over the second layer, the sulfate of the first layer will be uniformly acting, and therefore the pressure distribution diagram is rectangular. So in this case, I just thought this surcharge over here. What is the intensity of this surcharge? The intensity is Q is equal to gamma 1 into H1. So here just have to consider that Q, and in this case, this Q will be uniformly acting throughout the volume, therefore the pressure distribution diagram is rectangular. Here, this is Q into Ka2. Now in the previous case, as the soil was same, therefore it will be Ka1. Whatever intensity you have obtained, same we can lower down. But here, this Ka2 is different for the different layer, therefore it will be a different one. Right? Then the pressure distribution diagram, that will be a triangular pressure distribution diagram due to the sulfate of the soil, and this is diagram number 3, this is diagram number 2. What is the intensity at the bottom? It will be Ka2 into gamma 2 into H2. Right? So there are 3 pressure distribution diagrams where the CG of an individual diagram will be at. Suppose we will assume that here this is A1, This A1 is acting at distance Z1. So Z1 is, what is Z1? Z1 is H2 plus H1 by 3. H2 plus H1 by 3. Then here it will be acting at Z2 is equal to H2 by 2. And here this Z3 is equal to H3 by, H2 by 3. Right? So here the total pressure PA is equal to A1 plus A2 plus A3. And therefore A1 is total PA is equal to, what is A1? A1 is half of Ka1 into gamma 1 into H1 square plus Q into Ka2 into H2 plus half of Ka2 into gamma 2 into H2 square. Right? Then what is Z1? Z1 is H2 plus H1 by 3. Then Z2 is H2 by 2. And Z3 is H2 by 3. Why it is H2 by 3? As it is a triangle and the CG of triangle is at H by 3 distance from the bottom, whereas this is rectangular where the CG of rectangle is at H by 2 distance from the bottom. Then here the total CG will be at this Z bar is equal to A1 into Z1 plus A2 into Z2 plus A3 into Z3 divided by total E. And it will be calculated in meters. Right? So with this, all the cases of dry cohesion-less soil we have covered. In the next class, we will see the various cases of the soil for purely clay soil. Right? So these are the numerical based on it. We will be discussed later. Right? Always remember that the ideal backfill for the retaining wall is a sandy soil, because sandy soil is the soil which actually, sir, हो गया है. Leave studio. So remember, always remember students, the ideal cohesion, ideal backfill for any type of retaining wall is considered as a sandy soil, because sandy soil doesn't retain the moisture. कभी भी पानी को पकड़ के नहीं रखता है, वो इजीली उसको छोड़ देता है. That is considered as a good draining material. Therefore, the ideal backfill is assumed as a sandy soil. Therefore, the sandy soil can be suggested to use over the field.